Get started. Anyone have any questions from yesterday before we dive into the last slide of set review? There's not a ton that we need to know. I'll let most of the curriculum speak for itself, making sure we're all on the same page. So far, the easy part. All right, last slide of set review. Subsets. I like to think of a subsets as very similar to less than or equal to when it comes to cardinality. So if we have a subset of a set called S sub 1, we're going to say that it's a subset if and only if every element of that subset is also a member of the original set. So there are less than or equal to exactly the number of members between those sets, and they must share everything in S1 must also be an S. And that way, the symbol for subset makes a little bit more sense. It's like a curved less than or equal to. A proper subset, we get rid of the equal, just like with less than or equal to, versus strictly less than, we no longer allow for equal to. A proper subset, which is exactly the same without the lower bar, just says that every element of S sub 1 is also an S, just like with a subset. However, now they cannot be equivalent sets. They cannot contain exactly the same members. Then we have the concept of a power set. So we have a set, we want all possible subsets of elements of the power set. So first question I'd have for you when looking at this S, ABC, how many members are in the power set? Haven't heard the right answer yet. All possible combinations of these elements.
6.
6 is closer.
8.
There we have the right answer. Answer is 8. Why is it 8?
2 to the power of 3.
2 to the power of 3. There are a couple ways to think about this, and it shows how combinatorics all relate to each other. So I like drawing this out just because it's very nice and useful. So we could first and foremost ask ourselves, how many subsets are there of size 0? How many ways are there to grab 0 of these elements? Exactly one way. You have the empty set. So we're going to say the empty set is a member of the subset. How many elements are there of size 1? Three of them. Each of the distinct elements, A, B, and C. How many are there of size 2? Also 3. What are they?
A, B, A, C, B, C.
A, B, A, C, B, C. And how many ways are there to grab 3? Exactly one way, A, B, and C. We end up with 1, 2, 3, 4, 5, 6, 7, 8 of them. How could we have figured that out beforehand? We said 2 to the third. If we say we raise 2 to the power of the cardinality of the set, we get that. So 2 to the third is 8. The other way we could have tried to break this down is recognizing that this is a row of Pascal's triangle. In terms of the number of elements baked within this, there's one element of size 0. There are 3 elements of size 1, 3 elements of size 2, and one element of size 3. So this is exactly the third row of Pascal's triangle. If you start drawing out Pascal's triangle, we have the 0th row, we have the first row, we have the second row, we have the third row, etc. And the sum of every element of every row of Pascal's triangle is 2 raised to the power of its row. And then every element here is the combination. This is 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So you break this down, you get a fun, easy way to think about combinations given a particular size. So if you're ever asked how many ways are there to, etc., you can write out the mathematical expression for it, which we could also go into. But this is, to me, a very intuitive way of seeing how all of this relates. Any questions on that? All of this will come in handy at some point. throughout the quarter. All right, so I like to keep things within the slide. So I like to at least have references. Again, you'll have access to all of these slides later. You don't need to write everything down word for word. What's more important are the ideas. Anything I draw on the board that is necessarily embedded or baked into the slides. So past a power set, we can look at a Cartesian product. A Cartesian product is taken over two sets, returns the set of tuples such that the first element of that tuple comes from the first set and the second element of that tuple comes from the second set. So if we want to do exactly the same thing or close to, where we have S1 and S2, let's say we have what is our Cartesian product? How would we get started with this? Yeah, we would want the tuple A1, and as soon as we have a tuple, we need to surround them by parentheses, and now order matters. So A1 is distinct from 1A, unlike in sets, where there were two elements, A and 1. It wouldn't matter the order in which you divulge them in your writing. But here, order does matter. We want to make sure that the A comes before the 1 because A is an element of the first set and 1 is an element of the second set. So again, the order of these does not matter because this is a set of tuples. So the order of the tuples does not matter, but the orders within the tuples does matter. So we can choose A and 2, B and 1, B and 2, C and 1, and C and 2. And that is our Cartesian product or cross product. Either one of those are equivalent. Questions on that? Any clarifications? All right. I originally had a lot more here, but I felt like it was much more important to just dive into the good stuff. And we'll address any concerns as we go. Large scale questions, anything from set reviews, set theory that you'd like me to go over, relate to, tie into something you've seen before? Okay. Away we go to the more fun stuff. All right, we're actually going to dive into the details of what I talked about yesterday. I started talking about the concepts of languages and alphabets, etc., but we're going to start to dive into this theoretical concept so that we can see exactly how programming languages are constructed. What are the building blocks they're made out of? And how do they relate to things that we've seen before in our own language? We need to be able to talk about this at a theoretical level if we are going to be able to discuss how to compile a language. So first we talked about an alphabet. Alphabet was just a finite non-empty set of symbols. We're going to call that capital sigma. As an example, we could just say, all right, A and B, only A's and B's in this language. So all strings that consist of A's and B's. So a string, just a sequence of those characters from the alphabet. We put them together and now they create what you might consider to be words, but we're going to call them sentences. Usually we'll denote these starting with the letter U. So we could say the string U is ABBA, the string V is BABBABBABBAABAAAA. I think I said that right. So we typically use the beginning characters for our alphabet, and we will use some of the ending characters for our strings. Just like you may have seen in intro CS courses, we can define some operations that we can take on strings. We can concatenate them, we can reverse them, we can identify substrings within your strings, return the length of a string, determine whether a string is a prefix or suffix of another string. So there are plenty of string operations we can take, just like you might be used to from any string library from any language you use. We will define, however, lambda to represent the empty string. I use all of this notation to be consistent with the book because I recommend, it's not necessary, but I recommend that people also follow along inside of the book when we go over some of these topics. So I will use notation that is consistent with the book, even though there are internet resources that will utilize different symbols representing different things. So one thing to note about this class is it's actually very difficult to find good online resources. It's a high-level course that there isn't a ton of good resource on. My recommendation is come talk to me. I know all this very well. So we're going to denote the reverse of a string, unlike you might have seen it before. We're going to use a superscript capital R to denote the reverse of a string. We're going to repeat a string, concatenate it n times. Then we're going to denote that with the string's name to the power of the number of times that we're going to repeat it. In Java, if you multiply a string times an integer, it just concatenates them, but you can imagine that instead it repeats the string that many times. It's kind of what it's trying to be gotten at with this superscript. Questions on this notation? Right. We can now start to define the sets of strings that we can get when we concatenate letters from our alphabet together. We're going to call this the star closure of the alphabet because we use this superscript star. So sigma star just tells us now all of these strings that we can get when we concatenate 0 or more symbols together. So the empty string would be concatenating 0. And then we could have any number of 1-character strings, 2-character strings, 87,216 character strings, does not matter. And we'll get into some questions about that in a bit so we can start thinking about what does that mean to be able to concatenate all of these characters together. We can define the positive closure to be the star closure minus the empty string. So we just, it's the equivalent of saying 1 or more symbols from the alphabet instead of 0 or more symbols. So plus just means any positive integer, and star means any positive integer and 0. So question I can throw out there for you. The alphabet size is finite. But when we take the star closure or the positive closure, it does not matter what the size of the alphabet is, as long as it's at least 1. But the star closure and positive closure are always infinite. Any intuition as to why there are an infinite number of possible strings? Yeah.
Because you could concatenate all the letters of the alphabet infinitely different ways.
Yeah, even if there's a single letter, the alphabet is only zeros. We can now map this onto the positive integers, or even the natural numbers we want to include 0. So there's a string that is 1 0, a string that is 2 zeros, a string that is 3 zeros, a string that is 4 zeros, 5 zeros, 6 zeros. Just take the size of that string and map it onto the positive numbers. And now there's no positive number that you tell me such that there's not a string of that length, even though there's only 1 character in the alphabet. You can do exactly the same for an alphabet of size 2. there's at least one string of every possible size, so you can map them onto another set that has an infinite number of elements, the positive integers. So now that we have this concept of a star closure, the star closure is a really important one. The positive closure is minimally important in terms of what we're going to talk about, just because you can define one in terms of the other. Now that we have the concept of the star closure, we can now define what a language actually is, which is a strictly defined subset of that star closure. We're going to say that there are some strings in this star closure of this alphabet that are in this language, and there are some strings that are not. To differentiate, when we say a string that's in a language, that means a sentence of that language. So we can say string and sentence a bit similarly. So as an example, we could say the alphabet is A's and B's, and the language is NA's followed by NB's. There are some elements of the star closure of that alphabet that are sentences in this language, and there are some that are not. What's an example of something that's in this language? String that's, or a sentence that is in this language.
AB.
AB, for n equals 1. What's another?
AABB.
AABB, n equals 2. How about the empty string? Is that in the language? N equals 0? Yep. If we wanted to write this out, so let's start with just the star closure of the alphabet. If we wanted to write this as a set, how could we somehow determine or write what is the star closure of this alphabet? Where would we start? How could we order this in some way that is useful?
When we put the empty set in the circle,
We would put the empty string, yes.
You would go for N1 and then hitting.
This is for the alphabet. Just for the alphabet, not quite for the language yet.
Let's do A then.
Yeah, so we can start with all strings of length. These are all the strings of length 0. A and B are all the strings of length 1.
AB.
A, B, A, and B are all the strings of length 2. And at this point, we could probably just add an ellipse, saying that this pattern doesn't really stop ever. Note that if I went in terms of the ordering of the number of the length of the string, this is complete. But what if I choose to try to do this in alphabetical order? Does that work? If I defined a string that starts out with lambda and then goes to A and then AA and then AAA and then AAAA. If I add an ellipse here, am I ever going to get to B? Am I ever going to get to AB? No. So that's one interesting problem with infinity, is depending on your ordering, you may have something that is complete or something that is not complete. Even though this goes on forever, it doesn't get to some aspect of the language that needs to be gotten to at some point. So think about your orderings. We'll talk about that actually a lot later in the class, but it shows up in some pretty fun, mind-bending ways. We talked about some examples of sentences in L. This was the empty string AB, AABB, AAABBB, etc. How many sentences are in the language?
Are you for infinite?
Yeah, that's the right answer. There are an infinite number of strings in this language, sentences in this language. Just like there are an infinite number of strings in the star closure of the alphabet. This is a fun question for later. I don't expect this to make full sense until we go over it, but are there more sentences in this language, or elements in the set of the star closure of the alphabet?
The elements of the set.
It's a good guess. The answer is they're exactly the same. And we'll go into why later on in this course. If that doesn't seem right to you, we'll come back to that. It's a bit mind-bending, but I'll have that make sense by the end of the class. Examples of strings that use the alphabet. So they're part of the star closure of the alphabet, but are not sentences in this language.
Just a.
A. Yeah, we need the same number of A's as there are B's that follow. If we just have A, there's one A and 0 B's. What's another example?
B,
Just B. Another kind of example?
AA,
AA, 2 A's followed by 0 B's. What about BA? Same number of A's and B's, but now the B's come before the A's. Yeah, that's not in the language either. Languages are sets. We can start to define the union, intersection, and difference between languages. We can define the complement of a language. Complement of a language, the universal set for this complement is the star closure of the alphabet. So anything that could be constructed with that alphabet that is not a member of the language, not a sentence in the language. We can define the reverse of a language. If we were to take every possible string that is a member of that language and reverse it, then it would be a member of the reverse of the language. So to give you a sense of what this would be, what is the reverse of English? What is a sentence in the reverse of English? I. That's true. There's a word I, and if you reverse that, it is still I. It is a 1-character palindrome. Race car, a longer palindrome.
IH. Wait, right? IH would count.
Sorry? Yeah, IH, like high reversed. Yes. So it doesn't have to be a word in English to be a word in the reverse of English. If you want something that's really long in a palindrome, you can take no sir away a papaya war is on. Or there are longer ones, but that's the long one I know. But it doesn't have to make sense. So I would be in the reverse of English as well. So here's mathematical notation. The reverse of a language is all strings W sub R or superscript R such that W is in the length. All reversed strings such that the original string was in the language. We can define the concatenation of two languages. If we take an element from the first language and an element from the second language and concatenate them, then that string is a member of the concatenation of the two languages. So L1, L2 are all strings XY such that X is a member of L1 and Y is a member of L2. What's an example of this in English? If we had L1 is English and L2 is English. Sorry?
What would it be like? We're like down or something like that? Or
Could be some kind of, we don't need to concatenate. It would be like do not.
okay.
Do is a legal English word, and not is a legal English word. Shove them together, do not. Hi, same word, can be exactly the same. If you wanted to take L1 is English and L2 is what's some language that one of you knows that's not English.
Oh,
Yeah, Haiola. Now we have a string that is, if L1 is English and L2 is Spanish, then and toss them together. A word from English, word from Spanish, concatenate. We can now say we can concatenate L with itself n times and define L to the n. L to the 0 is always defined to be just the empty string, regardless of what the language is. L to the 1 is L, and other than that, you have L squared, L cubed, etc. This would be all, like L cubed, if L were English, would be all legal concatenations of 3 English words. We can define the star closure of a language. This is just the union of all elements of L to the n. All possible n union together. And you have the positive closure of a language as just the star closure of a language minus L to the 0. Now, lambda is only in the positive closure of the language if lambda was in the language in the first place. But lambda is always in the star closure of the language. Questions on any of these definitions? Do these make intuitive sense? Any further explanation anywhere? Yeah.
So for the reverse of the language, if you have something that reverses to another string that is in the language, does it necessarily have to be the same string you started with, or can it just be something else that also works in the language?
I followed you for the first half.
So if I reverse.
So you have a palindrome and you reverse the palindrome. So it's both in the language and in the reverse of the
The
language?
same word,
Yeah,
right?
yes.
Could I have something? Never mind, I just figured out the logic. I'm just.
That is certainly not true. All right, next thing we're going to talk about is grammars. We use grammars kind of as a lookup to determine whether a sentence is well formed with respect to the language, whether it is syntactically correct. So we could start with English. So an English grammar, we might say, this is an example grammar, we're going to define the concept of a sentence as made up of the concept of a noun phrase followed by the concept of a predicate. You can think of this kind of like objects and how objects break down into their components. You might have some complex object that has 2 fields, a complex object and a complex object, except now we have an ordering associated with that as well. The noun phrase must come before the predicate because this is a string and order matters. We can further break down these ideas into further components. So a noun phrase can break down into an article followed by a noun. A predicate, we're going to simplify into just a verb. An article breaks down into the exact string the or the exact string a. And a noun will break down into the exact string boy or the exact string dog. Verb, the exact string runs, the exact string walks. So a very simple language. There are only 6 words in this language. So, ignoring the fact that there are no spaces in any of these words, so ignore white space for the moment, but is the boy runs a legal sentence according to the grammar? How could we figure this out or derive this from this grammar?
Maybe starting from the smallest part, from the most broken down, and then go to the largest.
Yeah, you can kind of try to, starting here, go backwards, say the, well, that's an article, so we could kind of, I'm just going to shorthand this to article. Boy, shorthands to noun. Runs, shorthands to verb. Verb, go back to predicate. Article, noun, in that order, as we have it here, goes to noun phrase. And noun phrase predicate becomes sentence. And since we were able to derive sentence by itself here at the beginning, then we could say that this sentence is well formed. There's nothing that says you couldn't go the other way. Starting with sentence, make a noun phrase and a predicate, break the noun phrase down into an article and a noun, and there exists some article and noun and verb that now creates the sentence that is the query. So once we can derive the sentence, then we would terminate and accept. So you can work either way, top down or bottom up. Questions on how to read this grammar and how this grammar can be used to determine whether a sentence is well formed? What's a sentence not in the language? Using the 6 words that are in the language.
Dog walks a boy.
Dog walks a boy. I love this. Does it kind of make sense? So is there any way to map sentence down into these 4 components? Or to bring these components back up to make just sentence?
So like noun, verb, article.
Yeah. Is there any way? So dog has to be a noun, walks has to be a verb, a has to be an article, and boy has to be a noun. There is no possible way to construct sentence in a bottom-up way from that. You might be able to, if this were ordered a little differently, make sentence followed by a word or two, but that doesn't matter. You would need to just be able to derive sentence by itself at the beginning. Or take the concept of sentence and starting with just sentence, break that down into exactly these 4 words in exactly this order. And there is no way to do that. So this is not a sentence in the language defined by this grammar. So yes, grammars define languages. There are now a subset of sentences from these 6 words and orderings. If you could do that forever, some subset of that is going to be the language defined by this grammar. All such constructs that we could make by following these rules. All right. We could say grammar is complete if it defines every possible sentence in a language. So one thing that I could ask you is write a grammar that defines this language, that disseminates every string in this language. And there are going to be a number of grammars that might work for this, probably an infinite number of such grammars, but there are also an infinite number of grammars that are wrong. Ways for a grammar to be wrong if there is a string that is in the language that your grammar cannot produce. Or if your grammar can produce a string that is not in the language. So we want to, for all strings that are in the language, there may be an infinite number of them. If the grammar can generate that string, it's in the language defined by that grammar, that's great. If the grammar cannot generate the string, it's not in the language defined by the grammar. So a grammar maps to a language. There is only one language that a particular grammar represents, but for a given language, there may be multiple possible grammars that can define it. In general, how you want to construct a grammar, start with the most general concepts and define them in terms of more specific concepts, then define those in terms of more specific concepts, and then define those in terms of more specific concepts until you get down to string literals. This is very much like how you make objects. Eventually, all objects break down into primitives. Since we can't store the concept of an object in memory, really, we can as a construct, but we can't do an operation on that without breaking it down into its primitives, which is what a CPU can actually calculate and work with. So maybe we would have a person object, and that person object breaks down into an age and a height and a weight. Who knows? Those are the three important things about a person. But we could define each of those in terms of the age is just an integer, the height and the weight are still integer. The feet, inches, meters, centimeters. Doesn't really matter how you do it, but it would break down further until you get to those primitives. A grammar is exactly the same, but your strings are your primitives. And anything in those angle brackets is something that is a more general concept. So the goal of a grammar is just to reduce each concept down into its irreducible building blocks, the concepts of primitives in programming languages. Fun question I have for you. Where we're going with this is that grammars, of course, exist for programming languages that you've used and seen. How complex do you think they are? How much logic would you need to be able to define a grammar for a programming language like Java?
More than I want to think about.
I can't, no, I don't want to play this game. I'll just show it to you. All right. Here, directly from Oracle's documentation, is the grammar for the Java programming language. A lot of these terms are going to make sense if you have, you've seen, so an identifier. What is an identifier? Anyone remember what the concept of an identifier is? Anything that can either be a keyword, a variable, something that when it's constructed has some meaning, even if it's user defined. So qualified identifiers, those are the ones that start with dot. And you'll see that there is quite a bit here. We have lists of types, basic types, reference types, non-wildcard types, access modifiers. A bunch of definitions of exactly what strings represent which ideas. And you can see now that a statement is made up of a block followed by a semicolon. And can be any one of these. Now these are all options for statements. And you probably used most of this, but there's our list of assignment operators, how expressions are formed, logical operators, what's allowed infix, what's allowed prefix, what's allowed postfix. But that's the end right here. So with these rules, just as such, we can represent all computable logic. We can represent any program that you have ever written in Java, that anyone has ever written in Java, or that anyone could ever write in Java. There are an infinite number of those possibilities if it's defined by a fairly succinct grammar. Given the complexity of the language, given the complexity of what you can do with it. The grammars are generally significantly simpler than what you can do with the grammar. Questions, comments, or thoughts on that? All right, so let's give you the formal definition of a grammar. It's going to be a quadruple or a four-tuple, however you'd like to state that. I'm not a huge stickler for the formal language definitions of things, as long as the intuition is there. So don't feel like you need to memorize exactly how to relate this, but this is the information that if you were writing a program for a grammar, this is the information that you would need to give that program with regards to defining that grammar. So V, the variable objects, these are the left-hand sides, anything in angle brackets on that last grammar. So sentence, noun, phrase, predicate, article, noun, and verb were all variables and or what I'm going to call non-terminals. They're the concept of objects that are not primitives in a programming language. T is the set of objects we're going to call terminals. These are the strings, the, boy, dog, runs, walks, a. Those are your terminal symbols, or in a programming language, your primitives. We're going to have a special member of our variables set that we're going to call the start variable. This is where we must begin every derivation in that grammar. So we had to start with sentence and eventually construct a sentence out of it. So sentence was that start variable. Then we have the set of productions, P. Those are all of the rules. So we have non-terminal, arrow, some non-terminals, non-terminal, arrow, terminal, something along those lines. So object, primitive, object, 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 etc. But each one of these is one of those. So here's a rule, 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 and here's a rule. Those are all of your productions. So if you can define that quadruple, then you have the definition of a grammar. And again, if you're doing this programmatically, this is a set, this is a set, this is a single string, and then this would be a set. Thoughts on this? Questions, clarifications?
The production defines the rules.
Yes. Okay. Yeah, productions are another way of thinking of them is just to say they are the rules. We call them productions, but calling them rules would not be wrong. And then assume without further mention that the sets of non-terminals and terminals are both non-empty. There must be at least one non-terminal and must be at least one terminal, and they must be disjoint, meaning they don't share members. We can't have a variable that is both a terminal and non-terminal. We can't have something there that is neither a non-terminal nor a terminal. It's either one or the other. It's either an object type or a primitive type. You can't define something that's both. Okay. Here's a grammar. What is the language defined by the grammar? Let's start there. So just two productions. We have our quadruple. We have our list of productions. You can ignore the second half. Then, so we can write is just some additional stuff, giving you an example of a derivation. I would choose to do this is we're going to start with the start non-terminal, and I'm just going to start building a tree. With this S, there are two options. There are two things we can do with this S. We can either go directly to lambda, and if we do that, we just end up with the empty string. So the empty string is in the language defined by this grammar, because there is a legal way of getting there. I'm going to apply the S arrow ASB to get down to this ASB here. From here, we could either terminate and go to lambda. If we take this S and go to lambda, we get the string AB. On the other hand, if we apply and turn this S into another ASB, the A and the B already existed, and this S becomes ASB. This just becomes a recursive definition. So you can continue to take just the characters that are here, A, A, B, B, and terminate, and define another of them, A, 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 S, B, B, B. At this point, I'm hoping that this process, which goes on forever, is becoming a little bit more clear. What is the language defined by this grammar? What are the set of strings that it could produce? The same language we talked about a couple slides ago, A to the N, B to the N. SEN. Does everyone see that? This is the n equals 0 terminal. This is the n equals 1, n equals 2. And this process would just continue down this kind of linked list like tree that only has if you go right, you reach a leaf. And if you go left, you can continue to go left forever. As soon as you go right, you're done. Yeah.
Did that rule ever break if we had, or if we just stopped at like n equals 2, but had gone to the left? So we ended up with AAA SBBB.
We could never derive AABB again.
Correct, but
Yeah.
could our language then hold the AAA SBBB if we did not choose the S as lambda? If we just left it as it.
Yes. So the S, this is not a terminal. This process we keep going. We would have a right here and a left here, and this would go to AAA, B, 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 and this would go onwards to derive every single one. So this would be the n equals 3 row. So if we wanted to generate, we can't stop at any non-leaf.
Okay.
Yeah, at an internal node, we can't just decide we're done because there's still a non-terminal left in that derivation. There's still an object that's left. You can't feed an object to a CPU and hope that it knows what it's doing. You have to feed only primitives, only things that it knows how to evaluate. So this is the equivalent of breaking that down into those primitives. Really good question. Anything else? All right. How can we prove something like this? How can we prove that this language generates A to the N, B to the N? There are an infinite number of strings. I wrote out a tree that shows that I could generate n equals 0, n equals 1, n equals 2, n equals 3. How would I go about proving that I could make A to the 100,000, B to the 100,000? I don't want to draw out that tree. We don't have that kind of time. I'd still be here at the end of the quarter. Back to discrete. What proof method?
The assumption. Or whatever it's called. Where you use K and then you say K plus 1.
Yep,
And then you.
it is. It is exactly that. It is induction.
Oh, okay.
Yes. Yes, we could absolutely use induction. We could show that the string n equals 0 is in this language with a derivation. And we could say if a to the n, b to the n is in the language, then a to the n plus 1, b to the n plus 1 is in the language. Given that that was the case, from a right child, go to its parent, go to its left child, go to its right child, and you could generate the next one. So now you have a way of iterating through an infinite tree, basically. And that would work for any n. Really annoying that we're stopping right here, because the very next thing we're doing is an example. So I'll come back to and explain this in a bit more detail at the start of next class, and we'll dive into some more practice problems. I don't like talking to you this long. But I'll see you tomorrow for that.
Go more with it. I'm thinking of
I have office hours starting now, if anyone has anything to discuss.